All right, so we're going to cover 12.3 and 12.4 today. The last two sections for this class for this semester. All right, so 12.3 is about measures of dispersion. So we have two different things that we're going to learn how to calculate. One of them is really simple and one of them is kind of complicated. So the range is really simple. It's just when you have a data set or a list of numbers, you just take the largest number minus the smallest number, and that equals your range. Then for the standard deviation, okay, so this is kind of measuring, it's measuring dispersion or how spread out your data points are from each other. All right, so this is the formula for calculating that. And we're going to use a table to actually calculate it. All right, so the X with a line over it, I read that as X bar, which means it represents the mean. So let's see. So let's just start by calculating the range for number one. So it's just a list of 4 numbers. And so the largest one is 23 and the smallest one is 8. So 23 minus 8 would be 15. So 15 is the range. All right, and then in order to calculate the standard deviation, we also need to calculate the mean. All right, so the mean X bar, 12 plus 8 plus 15 plus 23, and add all those up and then divide by 4. So that equals 14.5. Okay, so we're going to use this table. We're going to do X minus X bar. So we're going to do 12 minus 14.5, 8 minus 14.5, 15 minus 14.5, and 23 minus 14.5. All right, so that would equal negative 2.5. And this would equal negative 6.5. And this would equal 0.5. And that would be, let's see, 8.5, right? Okay. And then we want to square that. So we're just going to square each of those. So that equals 6.25. $42.25, 0.25, and 72.25. All right. So then what we're going to do, so this this big symbol here that looks kind of like an E. That's actually the Greek letter sigma. And what it means is it means the sum of. So the sum of x minus x bar squared. So that means we're going to take that last column of numbers, and we're going to add them all up. So 6.25 plus 42.25 plus 0.25 plus 72.25 equals 121. All right, so we've done the sum of all those. And so to get the standard deviation, it's equal to the square root of that sum, which is 121, over n minus 1. So n is the total number of data values. So in this case, n equals 4. So 4 minus 1. All right, which is the same thing as 3. So we can put this into the calculator, and you can either put parentheses around 4 minus 1, or you can just put 3, either way. All right, so to get the square root, it's right above the x squared button. So you have to press second, and then you have to press the x squared button. And that'll give you the square root. And then we can just put in 121 over, and then like I said, you could either put parentheses 4 minus 1, or you could just put 3. All right, so the standard deviation is approximately equal to 6.35. All right. So number 2, let's calculate the range. So the highest is 30, the smallest is 5, so 30 minus 5 equals 25, so the range is 25. And we also need to calculate the mean, x bar, 27 plus 14 plus 30 plus 5 plus 19, and then divide all that by 5. And that equals 19. So 27 minus 19, 14 minus 19, 30 minus 19, 5 minus 19, and 19 minus 19. All right, so that equals 8, negative 5, 11, negative 14, and 0. And then we're going to square each of those. So that's going to be 64, 25, 121. I think that's like 196, maybe. Yeah, 196. All right, then we're going to add all of those up. So 64 plus 25 plus 121 plus 196 equals 406. Okay. So the standard deviation equals the square root of 406 over, so in this case, n is 5 minus 1. So the square root of 406 divided by 4. So the standard deviation is approximately equal to 10.07. All right. Okay, so in this case, we have a histogram. We should probably make, I didn't put in a column for frequency, but we can do this with using the frequency to make it a little bit easier. So let's see. So let me just, maybe I'll just write a new table over here with the frequency. All right, so we have 1, 1, we have 2 2s, we have 3 3s, we have 2 4s, and we have 1 5. All right, so let's calculate the mean by doing x times frequency. So multiply across. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 2 is 8, 5 times 1 is 5. And then we can add those up. So that'd be 14 to 16, that'd be 27. Add those up. That's going to be 10. Yeah, 10. So the mean is 27 divided by 10, which equals 2.7. Oh, wait, that's not 10, is it? That's 9. Yeah, 10. So that makes that 3 is the mean. Okay. So then we can do x minus x bar. So 1 minus 3, 2 minus 3, 3 minus 3, 4 minus 3, 5 minus 3, which is -2, -1, 0, 1, 2. Then we can do, what we're going to do is we're going to do the frequency times that squared. So that would be 1 times -2 squared, 2 times -1 squared, 3 times 0 squared, 2 times 1 squared, and 1 times 2 squared. So let's see, that's going to be 4, 2, 0, 2, 4. And then we can add these up. So that's going to be 12. So our standard deviation equals the square root of 12 over, in this case, n is 9. So 9 minus 1. So the square root of 12 over 8. So it's approximately 1.22. And oh, in this case, the range, you would just do 5 minus 1, which would be 4. All right, number 4, let's convert that stem and leaf plot into our table. So we have 12, 15, 20, 24, 24, 31, 37, and 48 is our data set. So if we did the range, that would be 48 minus 12, which would equal 36. So that would be the range. And then let's calculate the mean, x bar. 12 plus 15 plus 20 plus 24 plus 24 plus 31 plus 37 plus 48, and divide all of that by how many? 1, 2, 3, 4, 5, 6, 7, 8. So that equals 26.375 for the mean. Okay. All right. Okay, so 12 minus the mean is negative 14.375. And square that is 206.64. 15 minus the mean and square it is 129.39. 20 minus the mean and square it, 40.64. 24 minus the mean is squared 5.64, 5.64, 31 minus the mean squared 21.39, 37 minus the mean squared 112.89. And then 48 minus the mean squared is 467.64. So we have to add all of those up. Equals 989.87. All right. So the standard deviation equals the square root of 989.87 over 8 minus 1. And that's approximately equal to 11.89. So the higher the standard deviation is, the more spread out your data is. All right, so that's the end of 12.3. And then we will go to 12.4. So 12.4 is an introduction to the normal distribution. The normal distribution is it's pretty much how most data is distributed. Okay, meaning, so it could be, heights or weights or just about anything. But the majority of the data points are going to be in the middle. That's why you have the high point in the middle. And then you have a little bit that's on the small side, and you have a little bit that's on the high side, but the majority of it's in the middle. So you have the mean. The mean is right in the middle. And then you have the standard deviation. So 68% of the data is in the middle within one standard deviation on either side of the mean. And then within two standard deviations, you have 95% of the data. And within three standard deviations, you have 99.7. So it's 68, 95, and then 99.7. Okay, so for example, if we suppose that the weights of full-term newborns are normally distributed with a mean of 7.5 pounds and a standard deviation of 1.6. All right, so the mean, that's your X bar, is 7.5, and your standard deviation is 1.6. In that case, what is the weight of a baby who is 2 standard deviations above the mean? So you would take the mean plus 2 times the standard deviation. 7.5 plus 2 times 1.6 equals 10.7 pounds. And what is the weight of a baby that is 1/2 of a standard deviation below the mean? So the mean minus 1/2 times the standard deviation. So 7.5 minus 0.5 times 1.6 equals 6.7 pounds. All right, so if we were to like fill in the numbers on this graph, we'd have 7.5 in the middle. And then if you take 7.5 plus 1.6, that equals 9.1. Plus another 1.6, that equals 10.7. Plus another 1.6 equals 12.3. And then on the other side, you can do 7.5 minus 1.6 equals 5.9. Minus another 1.6 equals 4.3. Minus another 1.6 would be 2.7. Okay. Okay, so then the question is, what percentage of babies weigh between 5.9 and 9.1 pounds? So what percentage of babies are in this range here? So that's one standard deviation on either side of the mean, so that's 68%. And then what percentage of babies are between 4.3 and 12.3? Okay, so between 4.3 and 12.3. So between 4.3 up to 10.7, that would be 95%. And then we would want to calculate what is the amount that's in that little extra region. So let's see. So between 2.7 and 12.3 is the 99.7%. So do 99.7 minus 95. And that would, and so when you do that, that's going to give you the percentage that's in these two sections right here, this section and this section over here. And then you want to divide that in half to get the amount that's only in one of those sections. So 99.7 minus 95, and then divide that by 2, and that gives you 2.35. So the amount in one of those sections is 2.35. So to answer this question, I would say 95% plus 2.35%. So that equals 97.35%. And what percentage of babies weigh more than 9.1 pounds? Okay, so we already know that this section is 2.35%. Let's see. All right, so more than 9.1. So we're looking at all of this. So I think one way we could do that is we could take 100% minus 68, and that would include all of that region that I just highlighted, plus the matching amount on the other side, right? But then divide that by 2. So that would be 34 divided by 2 would be 17%. Let's see, is that right? Does that sound right? Sounds right. Yeah. Oh, wait. Oh, it should be 32. Yeah, 32 divided by 2, not 34. Okay. Like it sounds almost right, but something seemed off. 32 divided by 2 is going to be 16%. So yeah, that's right. Okay. All right. Okay. So then the z-score is the number of standard deviations that a value is away from the mean. So if z is positive, that's when it's above the mean. If it's negative, that means it's below the mean. All right, so to calculate the z-score, it's equal to x minus x bar over the standard deviation. So suppose the ages of full-time college students are normally distributed with a mean of 22 and a standard deviation of 1.5. Okay, so x bar equals 22 and s is 1.5. What is the z-score of a 29-year-old student? Okay, so z equals 29 minus 22 over 1.5. All right, and you can put this directly in your calculator. Just make sure you put parentheses around the numerator so it knows that that whole thing is going to be divided by 1.5. Okay, so that's approximately 4.67. What is a z-score of a 19-year-old student? So 19 minus 22 all over 1.5. That equals -2. And what is the age of a student with a z-score of 0.5? So 0.5 equals x minus 22 over 1.5. So to solve for x, I will start by multiplying both sides by 1.5. So 1.5 times 0.5 equals 0.75. So 0.75 equals x minus 22. So then just add 22 to both sides. So 22.75 years of age equals x. All that is it. That's the end.